In statistics, a sequence, or a vector, of random variables is homoscedastic if all its random variables have the same finite variance. This is also known as homogeneity of variance. The complementary notion is called heteroscedasticity. The spellings homoskedasticity and heteroskedasticity are also frequently used. Assuming a variable is homosedastic when in reality it is heteroskedastic results in unbiased but inefficient point estimates and in biased estimates of standard errors, and may result in overestimating the goodness of fit as measured by the Pearson coefficient. A standard assumption in a linear regression. While I equals x I beta plus I equals 1 n display style y underscore I equals x underscore I beta plus epsilon underscore I equals 1 L dots n is that the variance of the disturbance term I display style epsilon underscore I is the same across observations, and in particular does not depend on the values of the explanatory variables x I display style x underscore I dot. This is one of the assumptions under which the Gauss-Markov theorem applies an ordinary least squares, OLS, gives the best linear unbiased estimator, blue. Homoscedasticity is not required for the coefficient estimates to be unbiased, consistent, and asymptotically normal, but it is required for OLS to be efficient. It is also required for the standard errors of the estimates to be unbiased and consistent, so it is required for accurate hypothesis testing, e.g. for a t-test of whether a coefficient is significantly different from zero. A more formal way to state the assumption of homoscedasticity is that the diagonals of the variance covariance matrix of display style epsilon must all be the same number. E I equals sigma 2 display style epsilon underscore I epsilon underscore I equals sigma caret 2, where sigma 2 display style sigma caret 2 is the same for all I. Note that this still allows for the off diagonals, the covariances E I J display style epsilon underscore I epsilon underscore J to be non-zero, which is a separate violation of the Gauss-Markov assumptions known as serial correlation. The matrices below are covariances of the disturbance, with entries E I J display style epsilon underscore I epsilon underscore J when there are just 3 observations across time. The disturbance in matrix A is homoskedastic. This is the simple case where OLS is the best linear unbiased estimator. The disturbances in matrices B and C are heteroskedastic. In matrix B, the variance is time-varying, increasing steadily across time. In matrix C, the variance depends on the value of x. The disturbance in matrix D is homoskedastic because the diagonal variances are constant, even though the off-diagonal covariances are non-zero and ordinary least squares is inefficient for a different reason, serial correlation. K equals sigma 2 1 0 0 0 1 0 0 0 1 B equals sigma 2 1 0 0 0 2 0 0 0 3 C equals sigma 2 x 1 0 0 0 x 2 0 0 0 x 3 D equals sigma 2 1 rows 2 rows 1 rows 2 rows 1 backslash display style a equals backslash sigma caret 2 backslash begin matrix 1 and 0 backslash 0 and 1 and 0 backslash 0 and 0 and 1 backslash end matrix backslash b equals backslash sigma caret 2 backslash begin matrix 1 and 0 backslash 0 and 2 and 0 backslash 0 and 0 and 3 backslash end matrix backslash c equals backslash sigma caret 2 backslash begin matrix x underscore 1 and 0 backslash 0 and x underscore 2 and 0 backslash 0 and 0 and x underscore 3 backslash end matrix backslash d equals backslash sigma caret 2 backslash begin matrix 1 and backslash row caret 2 backslash row and 1 and backslash row caret 2 and backslash row and 1 backslash end matrix. If y is consumption, x is income, and backslash display style backslash epsilon is whims of the consumer, and we are estimating while I equals beta x I plus I backslash display style y underscore I equals backslash beta x underscore I plus backslash epsilon underscore I comma. Then if richer consumers' whims affect their spending more in absolute dollars, we might have v k r I equals x I sigma 2 backslash display style var backslash epsilon underscore I equals x underscore I backslash sigma caret 2 comma. Rising with income, as in matrix C above. Residuals can be tested for homoscedasticity using the Brush-Pagan test, which performs an auxiliary regression of the squared residuals on the independent variables. From this auxiliary regression, the explained sum of squares is retained, divided by 2, and then becomes the test statistic for a chi-squared distribution with the degrees of freedom equal to the number of independent variables. The null hypothesis of this chi-squared test is homoscedasticity, and the alternative hypothesis would indicate heteroscedasticity. Since the Brush-Pagan test is sensitive to departures from normality or small sample sizes, the Cohenker-Bassett or generalized Brush-Pagan test is commonly used instead. From the auxiliary regression, it retains the r-squared value, which is then multiplied by the sample size, and then becomes the test statistic for a chi-squared distribution, and uses the same degrees of freedom. Although it is not necessary for the Cohenker-Bassett test, the Brush-Pagan test requires that the squared residuals also be divided by the residual sum of squares divided by the sample size. Testing for group-wise heteroscedasticity requires the Goldfeld-Quant test. Two or more normal distributions n mu I sigma I backslash display style n backslash mu underscore I comma backslash sigma underscore I are homosedastic if they share a common covariance or correlation matrix sigma I equals sigma j turned a I j backslash display style backslash sigma underscore I equals backslash sigma underscore j comma backslash for all ij. Homosedastic distributions are especially useful to derive statistical pattern recognition in machine learning algorithms. One popular example is Fisher's linear discriminant analysis. The concept of homoscedasticity can be applied to distributions on spheres,